right, a most wonderful and beautiful and amazing good after morning, everybody. Yeah, it's sad times, isn't it? We are coming to the end with this course. The United Kingdom is, well, crashing out, or maybe not, or, you know, no. I think these were 8 no's from last night. So, times of uncertainties, and you have witnessed another time of uncertainty, because if you had looked at your email, you would have noticed that you got your Friday email today. So that was the change that I alluded to last time, which Chris obviously got really upset about. I'm not here tomorrow, so that's why I had to send it out today. Again, business as usual, you have another test coming up. And this is due then, or this week's test is due on Sunday night. Terms and conditions apply. Please, please, please make sure that you click on the right student number when you submit it. I had a student in my office this week who was very nervous, and he said it looks like that they have clicked on somebody else's. What's going to happen? Well, not a lot. It won't count for you if you click a wrong number, because the system doesn't know that you clicked on a wrong number, and then it doesn't know who you are. However, if you have submitted for somebody else, obviously they will get the mark. Even if you were pretty crap and scored them 0, it wouldn't make a huge difference to them, because only the best mark of all attempts will count. So it's no disaster. And you can repeat the test as often as you like. As I told you, this is a really, really good exercise for your exam. I understand you are the lucky winners with the exams, in that you have your last exam on the last day of the exam period, on the 14th of June, or is it the 15th? 14th, on the Friday. And that is the BI 308. But you don't have to worry about it, because if you do these online quizzes, and if you do go to my website, and the link is in the email, you have so much to practice. I will also send you a sort of a cheat sheet where it tells you exactly what you need to know for the exam. But then also, one of the issues is you are not, and it's an old story, you are not learning for the exams, because that stuff that you're doing is really for you to apply during your studies, so during the next 2 years. And then, if you are going to be a professional whatever scientist, this is the stuff that you need to know, right? It's and at one point you really do have to learn it, so you just as well learn it now. It's the easiest way. So I said that I'm going to revise a little bit on the kinetic stuff that we have done. So I hope, yes, it's coming up. Again, during the week I had a lot of issues with this thing, but luckily it seems to work. Revision kinetics. And we started with defining what is kinetics. Kinetics basically tells us how fast something, how fast a reaction, and reaction is here in the loosest sense, how fast a reaction happens, assuming that the reaction does happen. And the difference to thermodynamics, the topic that you all love, I know, the difference to thermodynamics basically is thermodynamics tells us whether or not a reaction happens. Kinetics tells us how fast this reaction will be. We differentiated between different terms, so rate, speed, and velocity. And we basically said that rate has usually a direction, whereas speed doesn't. And we looked at the general rate equation, where we said the change in, if we, for example, if we look at the consumption of a reactant, which I abbreviate here with A is consumed. A could be a reactant, could be a substrate, for example, in an enzyme reaction. A is consumed, and we said the rate with which this A is consumed, we can write this as basically dA over dt, which means that is the rate, a change in A, in the concentration of A per change in time unit equals minus k times A, the concentration of A to the power of m. And we said this k here, that is the rate constant. And m is the rate order. And one thing that I really, really want you to understand is that a rate order is just simply a number. It is a mathematical concept that allows us to write this equation. Only a mathematical concept. This rate order can be any number. It can be a positive number. It can be a fraction. It can even be a negative number. How would we actually interpret a negative rate order? What do you think? What happens if m is smaller than 0? What could that mean? It's possible, but what could it mean?
Negative.
That m is negative. If m is smaller than 0, what does that mean? If you need to explain that to, let's say, your grandma.
Oh, so m is negative?
That's a good point, yes. And your grandma goes, what? What? Oh, yeah, okay, m is negative, but would it go? That's, Astrid, that's a good idea, and yet not quite. A good idea. What would this rate equation look like if we put m negative? So rate equals minus k times let's say a to the power of minus 1, just for the sake. How else could we write this? Thank you. Equals minus k divided by the concentration of A. Yeah? What happens now to the rate? What happens to the rate if I increase the concentration of A? You're absolutely right. The rate becomes smaller if I increase the concentration of the reactant, if I increase the concentration of A. What do you call it when a rate gets smaller? What causes a rate to become smaller? What is this compound called? Thank you. Bingo. You are spot on. It's an inhibitor. The reaction becomes smaller when you increase the concentration of A. So, a negative m smaller than 0, indicates that there is an inhibitor. Does it make sense? So m can be anything. Don't confuse m with the molecularity of a reaction. Molecularity tells you how many molecules or how many partners have to interact with each other so that something happens. And sometimes you only need one thing. So for example, if you look at, for example, radioactive decay, you need one thing to do something so that something happens. Sometimes you need two entities to, for example, bump into each other. You can't have half a molecule. You can't have a negative molecule. God knows what a negative molecule is. So molecularity tells you how many entities have to work together so that something happens. Molecularity is either 1 or 2 for a reaction. It cannot be anything in between. Okay? Make sense? The order of the reaction can be anything. Can the order be 0? Yes. Then we have a 0-order reaction, and I come back to that in a minute. We then said, okay, let's look at this rate equation. Let's just simply write rate equals minus k times a to the power of m. And just for a moment, let's just simply forget about the negative sign. The negative sign indicates which way the reaction goes. So here we are talking about the consumption of A. And I probably should also mention K, the rate constant, K, is always, without any exception, is always positive. And I used to bring this example to the students that have you encountered Dr. Foster as a lecturer? No? You see, that's because that's a real shame. I absolutely adore Dr. Foster. And her first name is Kay. And I think Kay is always positive. She's such an incredibly positive person. Yeah? But unfortunately, you haven't encountered her, so you would not make immediately this connection. So let me tell you, K is always positive. If a student writes in an exam after 15 pages of wild calculations that, oh, my rate constant is minus 45, by definition, this student has just very eloquently demonstrated that they don't have an effing clue, right? Because K cannot be negative. So, 0. Ha! I don't have to read through 15 pages. Just skip that step. Okay? So K is always positive. Now, let's just simply, for simplicity's sake, just simply ignore this negative sign. So I put that here in the absolutes. So we are only looking at positive things. Because I show you how you can very easily figure out the rate order of a reaction. So we then have rate equals K times A to the power of M. And in order to get this M, to find M, what we need to do is we just simply log both sides. And it doesn't matter whether you use the log to the basis of 10 or ln or log to the basis of 6.857. Does anyone know what the number 6.857 stands for? Nor do I. I just made it up. So, and what do we get in this case? We get log rate equals M log A plus log K. And that gives us really nicely the equation for a straight line. Y equals mx plus c. So if we plot that, on the y-axis we would plot log A, and on the x-axis we plot, sorry, these two just threw me, log rate. And on the x-axis, we plot log A. and we would get a straight line. The gradient of this straight line gives us the rate order m. Where would we find k, apart from in her office? The y-intercept, is it k? That's log k. So this y-intercept would be log k. Can log k be negative? The way I've drawn it here. Can it be negative? Yes, absolutely. Why not? Log of a number can be either positive or negative. It's not a problem. But k can't be negative. Yeah? So how would a typical example look like for a question like this? You would be given, say, the concentration of a compound. And you would be given the corresponding rate. And the rate we said is usually given as concentration per time. And you would get this as well as data. And as soon as you see a setup like that, you know, aha, I need to get my calculator out and calculate log A and log rate. And this stuff then I can plot log rate, log A, as we've done it up there. And I can very easily find my m and my rate constant. And then give my answer and say life is exactly. Life is good. Life is splendid. So this is basically how you deal with a scenario where you have to find the rate order of a reaction. We then also discussed some special forms that bioscientists frequently encounter. And one of the things that we started with was if m equals 0, if we have a zero order reaction, we can very easily envisage how this would look like in our log plot. Log rate versus log A. How would that look like in the log plot? It's a horizontal line. Exactly. Like that. Yeah? There's nothing going on. This is actually, this means that the rate just simply is not affected by the concentration of the reactant. Whatever you throw in terms of A, the rate will always stay constant. Actually, you've discussed an example like that quite extensively, not in this module, in a different module. Where? Where did you deal with rates? Which module?
Biological chemistry stuff with.
Yeah, another one? Enzymes. So you plotted rate on the y-axis, right? Initial rates. Sounds familiar?
Yeah.
What did you plot for Michaelis-Menten on the or on the x-axis? You plotted the substrate concentration, didn't you? What happens at very, very high substrate concentrations?
The rate is high.
The rate is high. Will it further increase? You will get something like that, right? This means even if you increase the substrate concentration, your rate will stay absolutely flat, will plateau. This indicates that in this region here, the rate constant is 0. The rate order is 0. M equals 0. The rate is no longer dependent on the substrate concentration. That makes sense? So we said, okay, for M equals 0, we now can write change in A by change in time equals minus K times A to the power of 0 . And I told you that this is a differential equation. I didn't show you actually how you can solve this differential equation, but the solution for this differential equation would be the concentration of final concentration of A minus the initial concentration, the starting concentration, equals minus K times T final minus T initial. This would be the equation for a zero-order reaction. And of course, we are usually interested in what actually is the final concentration of A at a given time. So you can easily rearrange this equation. A final equals minus K times, and I just simply write T as the difference plus A initial. And the wonderful thing is, again, you see this is a nice equation for a straight line. Y equals mx plus c. So what we plot in this case here is the concentration of A, say millimolar or something like that. And on the x-axis, we plot time. Well, very often we say the initial time when we get started, that is 0, so we don't really have to worry about that. And what we would get in this case is a straight line. Which would look like that. Can it go into the negative range if we are thinking about A as a chemical reactant? Right? No, you're absolutely right. We can't have a negative A because a negative substance, it might exist as antimatter, but we haven't defined really biological systems in terms of antimatter. There might be universes out there that are full of antimatter, but let's not worry about that. So if it's gone, it's gone. So a typical reaction would look like that. When it's gone, it stays 0. Yeah? How would an example look like that you are dealing with? You would be given, for example, some time, and you would be given the concentration of A, and in this case, you would just simply do a plot like this here. The intercept, what does that give us here? The initial concentration. You are absolutely right. That's the initial concentration. What does the gradient give us? And here you could do a really nice trick. All you need to do is just do that for the gradient. What does that give us?
Minus k?
It gives us minus k. You are absolutely right. Minus k gives us the negative rate constant. Minus goes down. So then you have to convert it. Please don't give me a negative k. Yeah? What's the unit of k for a bog standard zero order reaction? Loud?
Concentration per time.
You are absolutely right. And I did not hear the question mark at the end, because you phrased it like concentration per time. No, it is concentration per time. Boom. Absolutely right. Are you happy with that? Make sense? Easy stuff. We then moved on to m equals 1. So this would be a first order reaction. So dA over dt equals minus k times a to the power of 1. And this basically means the more A I give, the more the higher my rate would be. Yeah, it's a linear relationship here. I told you that in this case, when you integrate this, you will end up with the equation ln of the final concentration minus ln of the initial concentration equals minus K times T final minus T initial. And again, you can very easily rearrange this equation so that you can nicely handle that. You can say ln A final equals minus K, and again, I just simply write T because T initial usually is set to 0. Not always, but it can be, plus ln A initial. And again, you see that this gives us the equation for a straight line. Y equals mx plus c. So if you want to work with a first order reaction in this case, what you plot is just simply, what do I plot on the y-axis? Oh, it's too easy. ln A, and on the x-axis, again, I plot time. And I would get something like that. Can it go into the negative range? Is it possible to have negative? What do you reckon? Who said yes? Who is brave? Vida? You're right. Of course it can go into the negative range because it's not negative A. It is negative ln A. So it can go like that. The intercept gives us ln A initial and the gradient again gives us minus K. What would be the unit for a first order reaction rate constant? Absolutely right. It would be time, just in general, time to the power of -1 or 1 over time. Doesn't matter how you do it. Yeah? One issue is that usually we are not terribly interested in ln A final. We want to know actually what is A final. And what you can do is you just simply simplify this equation. ln A final minus ln A initial equals minus K T final minus T initial. According to the rules of logarithm, you combine that. You can write ln A final divided by A initial equals minus K T final minus T initial. And what do you need to do in order to get rid of an ln? Yeah. You just simply E both sides of the equation. And what you have then, on the left-hand side, E and ln cancel out, and you've got A final over A initial equals E to the power of minus K T final minus T initial. And then it's not terribly difficult to figure out what A final is. Just simply bring that to this side. And you get A final equals A initial times E minus K times T final minus T initial. Okay? So in terms of how this would look like, you get, again, time. And you get A. The data for A. And if you know that it is a first order reaction, what you would do immediately is you would convert your data into, instead of A, you convert them into I know who's not here. Jane, get your, well, actually, no. We're finished. So what you would need to do is you would calculate ln in this case. Occasionally you come across, and then, of course, plot. Occasionally you come across a set of data in exam papers. You come across a set of data where it says, here's time, here is your concentration of A. Demonstrate graphically that this reaction follows a first order reaction. What I expect you to do in this case is to say, right, I know already from the way the question is phrased, I know already that this is a first order reaction. So good man. So all you need to do, if it says demonstrate graphically that this is a first order reaction, calculate your lna and plot that versus time. And then your argument is, it is a straight line if I do this plot, and love you too. And since it is a straight line, I know it proves that it is a first order reaction. If you are asked to demonstrate that it is a zero order reaction, all you would do is draw a similar graph You know it is zero order, so you would just simply plot A versus time. And you get something like that. Your argument would be it's a straight line, and it can only be a straight line in this kind of plot if it is a zero order reaction. It can only be a straight line in an ln versus time plot if it is a first order reaction. For a first order reaction, we also said we have another concept that is usually quite helpful, and this concept is called the half-life of a reaction. Please write half-life and not like a student in one of the exams. They came up with the expression low life. It's probably what they were thinking of me when they read the exam paper. And the half-life of a reaction, this only applies to first-order reactions. A half-life for any other reaction does not make sense. So only half-life for first-order reaction. Half-life of a reaction, and I write this usually as T half, equals ln2 over the rate constant. And ln2, if you are too lazy to calculate that, it's 0.693 over k. What is the unit for half-life? A lot of people struggle with that. What's the unit of a half-life? Or in general terms, time. Exactly. You have got k. In the denominator, k is 1 over time, so you have 1 over time, which gives you time. And in a way, the clue is in the t already, which stands for time. I have seen bad things in exam papers. There were seconds squared times the shoe size of the dentist. Things like that. And you think, ouch. So if you get that wrong, again, you demonstrate to me that you don't have a freaking clue about what's going on. Does it make sense? Here, on a side note, V versus substrate concentration. In your Michaelis-Menten plot, which you are explicitly forbidden to use regardless. Never, ever, under any circumstances, use a Michaelis-Menten plot to determine your enzyme parameters. Even if somebody's holding a gun to your head, don't use it. This region here has a rate order of 0, as we said earlier. This region here actually has a rate order of 1. But the really weird and bizarre thing with a Michaelis-Menten plot is that the rate order of an enzyme reaction changes according to the substrate concentration. So it shifts from O1 to 0 if we increase the substrate concentration. But that's something for another day. Any questions about that stuff? So regardless of what questions I throw at you, you should be absolutely fine with kinetics. Hey, hey! How cool is that? Thank you very much. See you potentially next week if you have any questions.